Hello! In this video, we're going to discuss the following theorem. For all integers n, the sine of n pi is equal to 0, the sine of n pi over 2 is equal to 1, if n is an integer of the form 4k plus 1, the sine of n pi over 2 is equal to negative 1, if n is an integer of the form 4k plus 3, the cosine of n pi over 2 is equal to 0, if n is odd, the cosine of n pi is equal to 1, if n is even, and the cosine of n pi is equal to negative 1 if n is odd. Now at this point, we know that cosine of pi over 2 is equal to 0, and we know sine of pi over 2 is equal to 1. We've also proven de Moivre's theorem, which tells us the following. It tells us cosine of z plus I sine z to the power of n is equal to cosine of nz plus I sine of nz for all complex numbers z and all integers n. So we're going to keep these results in mind throughout our discussion of these results. Now, to deduce these 6 results, we are first going to deduce a preliminary result, which will help us deduce all 6 of these results. And to see what that preliminary result is, let's first consider an arbitrary integer n. Well then, by de Moivre's theorem, we have the following. We have this. But then, we know that cosine of pi over 2 is equal to 0, sine of pi over 2 is equal to 1. So this is just 0 plus 1i to the power of m, which is just I to the power of m. And so what this tells us is that cosine of m pi over 2 plus I sine of m pi over 2 is equal to I to the power of m. And so we're going to keep this fact in mind. And now, we're going to consider 4 possibilities of what m could be. Either m is an integer of the form 4p, m is of the form 4p plus 1, m is of the form 4p plus 2, or m is of the form 4p plus 3. Right? One of these 4 has to be true. And so, what we're going to do is we're going to consider, in each of these 4 cases, what is cosine of m pi over 2 and what is sine of m pi over 2. Let's start with a case that m is of the form 4p. Well, in this case, we can write cosine of m pi over 2 plus I sine of m pi over 2 is equal to I to the power of 4p. And then, by properties of exponents, we know that this is just I to the power of 4 to the power of p. But I to the power of 4 is just 1, so this is just 1 to the power of p, which is equal to 1. And we can write this as 1 plus 0i. So overall, we have I to the power of 4p is equal to 1 plus 0i. And from here, we set the real parts and the imaginary parts equal to each other. So we have cosine of m pi over 2 is equal to 1, and sine of m pi over 2 is equal to 0. So this completes the case that m is of the form 4p. Now let's consider the case that m is of the form 4p plus 1. Now if this happens, then we can write cosine of m pi over 2 plus I sine of m pi over 2 equals I to the power of 4p plus 1. But then, by properties of exponents, this is just I to the power of 4p times I to the power of 1, or in other words, just I. And just like we did up here, we know that I to the power of 4p is just going to be equal to 1. So this is just 1 times I, which is equal to I, and we can write I as 0 plus 1i. So overall, this guy is just equal to 0 plus 1i. And now, setting the real parts and the imaginary parts equal, we have this. So now, let's move on to the case where m is of the form 4p plus 2. Now if this happens, then we can write cosine of m pi over 2 plus I sine of m pi over 2 is equal to I to the power of 4p plus 2. And now, by properties of exponents, this is just going to be I to the power of 4p times I squared, right? And we know that I to the power of 4p is just going to be equal to 1. So this is just 1 times 1 squared. But then I squared is equal to negative 1, so this is just negative 1, right, which is equal to negative 1 plus 0i. Right, so overall, this thing is just equal to negative 1 plus 0i. And so now we set the real parts and the imaginary parts equal, and we get this. So now let's consider our final case, which is m is of the form 4p plus 3. Now if this happens, we can write cosine of m pi over 2 plus I sine of m pi over 2 is equal to I to the power of 4p plus 3. Right? Then by properties of exponents, this is just I to the power of 4p times I cubed. We know that I to the power of 4p is just going to be 1. I cubed is equal to negative I. So this is just negative I. Or in other words, we could just write 0 minus 1i. Right? So overall, this thing is just equal to 0 minus 1i. So now we just set the real parts and the imaginary parts equal, and we get. So this is the preliminary result we have proven. We have proven, given any integer m, if m is of the form 4p, then this happens. If m is of the form 4p plus 1, then this happens. If m is of the form 4p plus 2, then this happens. Finally, if m is of the form 4p plus 3, then this happens. And so let me write that preliminary result back up at the top. So this is the preliminary result we have proven. Now, something else I should also mention is, if m is even, then the only cases that could happen are case A and case C. And if m is odd, then the only cases that can happen are case B and case D. Right? Because 4p is even, 4p plus 1 is odd, 4p plus 2 is even, 4p plus 3 is odd. So now, using this preliminary result, let's see how we can deduce each of these 6 results. To start out, let's give ourselves an arbitrary integer n. From here, let's show that sine of n pi is equal to 0. Well, to start, we're going to multiply and divide by 2. So we get this. And now, taking m to be 2n, now since 2n is even, this means we're going to fall under either case A or case C. But no matter which case we fall under, we see that sine of 2n pi over 2 is equal to 0. So this guy is equal to 0. So sine of n pi is equal to 0. So we have deduced result number 1. As for result number 2, this is actually immediate, right? Because in this case, we'll take m to be n. Well, since n is of the form 4k plus 1, well, that's the same thing as saying n is of the form 4p plus 1. So n is going to fall under case B. And we have sine of n pi over 2 is equal to 1, which is exactly what we want. So yeah, result number 2 is immediate. Result 3 is also immediate. So in case 3, we'll take m to be n. Since n is of the form 4k plus 3, that's the same thing as saying n is of the form 4p plus 3. So n is going to fall under case D. And we see that sine of n pi over 2 is equal to negative 1, which is exactly what we want. So yeah, result number 3 is immediate as well. As for result number 4, n is odd. So again, we're going to take m to be n, and since n is odd, this means we fall under either case B or case D. And no matter which case we fall under, we see that the cosine of n pi over 2 is equal to 0, which is exactly what we want. So yeah, result number 4 is immediate as well. As for result number 5, we want to show cosine of n pi is equal to 1 if n is even. So let's do some work for this one. We have cosine of n pi, and what we're going to do is we're going to multiply and divide by 2. So we have this. But we're assuming n is equal to 2k. So I'm going to replace n with 2k, So we get this, but then 2 times 2k is equal to 4k. So we get this. And now we take m to be 4k. Well, 4k is going to fall under case A. And we see that cosine of 4k pi over 2 is equal to 1. So this guy is equal to 1. So we have shown that cosine of n pi is equal to 1, which is exactly what we want. So we have shown that number 5 is true. As for result 6, it's actually going to be similar to result number 5. Right, again, let's write out cosine of n pi. We're going to multiply and divide by 2 once again. And then we're assuming n is odd in this case, right? In this case, we're assuming n is equal to 2k plus 1. So I'm going to replace n with 2k plus 1. So we have this. But then if I distribute the 2 across, we get 4k plus 2 pi over 2. And now in this case, we take m to be 4k plus 2. Well then, 4k plus 2 falls under case C. And we see that cosine of 4k plus 2 pi over 2 is equal to negative 1. So this guy is equal to negative 1. And so we have shown that cosine of n pi is equal to negative 1, which is exactly what we wanted. So we have deduced result number 6. And so we have deduced all 6 of these results. And there's one other thing I'd like to talk about before the end of this video. Now let's remind ourselves of the cosine and sine addition formulas. And using the fact that sine is an odd function, cosine is an even function, we can obtain the sine and cosine difference formulas, which will essentially just flip the sign. So combining the addition and difference identities with the 6 results we have just proven, we can obtain some other identities that we're all familiar with. Right? We can obtain these identities and also some other similar identities as well. So yeah, that's pretty much all I would like to talk about in this video. Yeah, that's pretty much it for this video.